Perfect. Thank you, sir. Okay. So yeah. So what does it look like? So here U will be the density of particles. So so far this is a PD. Okay. There's no probability yet. So what happens is that this U describes the density of particles or bacteria, if you want, who are emitting some chemicals C, and this chemical attracts other particles. So it's as if like bacteria were saying, okay, there is some food in that direction, follow me, and they all come together, attracted by this chemical. It also diffuses a bit. Okay, so that's the diffusion part here. So there are two effects driving bacteria: the fact that they are attracted by this chemical and emitting it, and the fact that they diffuse. Okay, so that probably would go in every direction. Right. So let me try to simulate this. So here I rewrote the equation. So by the way, there will be a very important parameter here, which is chi in blue. And so I'll just run some simulation on this Visual PD software, which is freely available on the internet. You can try it if you want. So this is in dimension 2, I should have said. So this dimension 2 in space. And okay, you will see why I chose this weird parameter here, or weird value for chi. So let me try to run it. Not really. Okay. Yes, it's coming. Okay, we'll try again. So I will restart it just to tell you. So I started from an initial density of particles. If I remember correctly, it was like a Gaussian centered at 0. Okay. So if you think about the heat equation, if you don't have this, you expect just your density to go flat, okay, in time. But like I said, there is this competing effect, which tends to attract all particles together. So there should be a competition between both. And what we see here for this parameter chi, so it seems to contract and then it goes flat, right? So it's as if the heat equation somehow was winning. So let's change a bit the parameter. So you see it was 846, 846. So I slightly increase it. Okay, I slightly increase it. And stay initial condition. And then, okay, the second time goes. Again. Too much suspense. Yeah. Okay, I will tell you what happens if you remember. So okay, this time first. So okay, so you see the Gaussian it concentrates, and then just the simulation blows up. I couldn't go any longer, but okay, you have to believe me that the concentration was getting really too high to concentrate at the origin, so it doesn't go flat anymore. Somehow you start to feel that there is a critical value for the parameter chi here, which there is no. So that's one thing that I wanted to point out before we start going into the particular approximation of this PD. Another thing that I will develop in the second part of the talk is about, so in the title is talking about suppression of blow-up, and this is a mechanism to prevent the blow-up that I've just shown you. And so here what I changed is that I added this green term here. So minus something, again, something very small. This value, this bad value of chi, for which I had blow up before, I just add this little term here, which a priori should prevent contraction, but by how much is not completely clear. Yeah, priori. But what you will see here is that prevents concentration. So maybe this time, yes. The same at the beginning, and then it goes flat again. Okay, and I will give you a more result about this later. Okay, so then you can play a little bit I will not run it. And you can do a lot of simulations like this. You can change a little bit the term here. The point is that if you have minus something u squared, you get rid of the block. At least in dimension 2, it works. Okay. And you can, again, I will show you a proper result, but you can take any value of chi here, it doesn't matter. But there's something strong going on here. Right. So just to simplify a little bit, or not simplify, a bit more compact, I'm using the fact that, remember, so on the second equation, I had Laplacian of C equals, or minus Laplacian of C equals U. So this is the Poisson equation on the whole domain. So I know that I can solve this, use the green kernel of the equation, and replace gradient of C here by K star U, where K is the gradient of the green kernel. Okay, so if you do the computation and it's classical, you get that the term gradient of C here should be K star U, where K is this kernel. D. And so what you immediately see is that this kernel, now in the it's singular, okay, in any dimension E greater than 2 will be at 1 over power of F. So it's singular, and also the sign here is important, so I will work with chi positive. The sign is important because it means that the particles are attracted to one another. Okay, so so what we'll be interested in, related to this equation is to have an approximation of the PD by a system of stochastic particles in interaction. Okay. So somehow I want a microscopic description of this phenomenon. Then I want to consider the empirical measure of this particle system, and I want to prove that converges to PD. Did several works on this topic already. I will try to explain. The second point that I'm interested in is, like I said, if I had, let's think of this as minus u squared, okay, or something related, I want to observe this suppression of blow-up, both at the level of the PD and at the level of particles. Okay, so that will be the second part of it. Okay, so I continue a bit with the introduction, just to start describing what is in fact, we go directly to the particle system. So the particle system that I will be using and considering working with make the following. So I told you that an interaction normally you don't think something singular or whatever, in that case, it's rather a standard theory that for this kind of n number of particles, and you have n SDs are coupled together. It's quite classical to say we'll not give up everything, but to consider that the empirical measure here converges as n goes to infinity to the solution. Okay. So here, of course, the difficulty, so this is known very well from the work of Smithman, for instance. Okay, you know that K, if K is Lipschitz, everything goes well. Here, of course, it's difficult because K, some kind of singularity, so that's where you start to get into troubles. Yes, so kind of result that we are aiming for our propagation of chaos results. We want to consider this empirical measure and prove that in some sense it converges to the PD as the number of particles goes to infinity. Yeah, like it said, so you have singularities. I should even say, and I will say a word about this at the end if I have some time. It's known since the works of Fournier-Jourdain, so it was 2016-ish, and more recently Fournier and Tardy. So it's one of the people I've been working with here. It's been known that in this particle system, for the Keller-Segel equation in dimension 2, there are collisions of particles. Okay, so that means that particles will touch, which is clearly a problem here because this is not defined if two particles are at the same place, right? So what is known also, I can give you a bit of the flavor of the problem here in a very schematic way, that if you can have two particles colliding, in fact, it's not too much a problem. In a sense, you can say, okay, don't stuck, just touch and then move away. Okay. But if K is large, so you know that at the PDE level you will have blow up. At the particular level, what Fournier and Tardy have proven is that okay, there are two collisions, which are no big deal, but then there is some integer which is clearly defined in terms of the number n of particles and in terms of Chi. It's very explicit. And for this number, if you will have, so let's call it K, you will have K collisions, so K particles colliding at the same time. And then for this very particular K, they get stuck. And at this point, there's no way to define the system anymore. It's done. So, okay. So there are really funny things and quite deep things which are happening here. But in any case, keep in mind at this stage that there can be collisions if I consider really this system. So it's really a difficult one. Okay, mention that. Quite many people have worked on this kind of similar problems. So the point of view that we will have here is slightly different. We'll get rid somehow of the difficulty of collision, although I will come back to it at the end. And what we will do is to say, okay, so without this guy here, this is a particle system that I wrote in the previous slide. And what I'm doing here is I'm modifying the interaction. Okay, so mu n here, sorry, maybe I should say it again. Mu n here is the empirical measure. So when I write this, it's really the equation from before. So I modify the interaction with this Vn, which is an approximate identity. It's an approximation of the Dirac. Okay. So you expect, if there is any limit for this guy, you expect that this would be a Dirac. And so somehow you recover the true PDE or the true limit. But at the particle level, you have simplified things because you have, I mean, everything now is smooth. And so you don't have, so in that case, for instance, you will have no collisions at all. All the interactions are smooth now. Okay, so if the interaction kernel is Vn star k, so okay, so this kind of interactions are called moderately interacting particles. It's been introduced by Schleger in the 80s, and then there have been quite a lot of work also in that direction. There will be a parameter here that I will use a lot, which is this alpha here, which describes Vn. So V here is a smooth density, smooth probability density. And then this alpha decides how picky it will be, how fast somehow it will go to the Dirac. Okay, so the questions I will ask here is how this mu n converges to the PDE, and in particular, I'm interested in obtaining a rate of convergence for mu n, and also in which sense. And the second part, the second part will be about suppression of blow-ups. We'll add this P of ut term in the PDE, and I will try to interpret it also in terms of particles. And consider the fact that I'm trying to give you results about the fact that there is no blow-up anymore in certain cases. All good? Mm-hmm. Okay. So the first thing concerns the PDE. So this is not something very difficult, but there are a few things to mention here. So the setup will be the following. So U0 is my initial density. So it's a density first. And I will assume that it's in some Lebesgue space, okay, and R, with R larger than the dimension. Okay, and what you can do just simply by doing a fixed point argument you can prove that there is a solution U to the Keller-Segel PDE locally in time. So I will always say, okay, here there exists some time t, okay, for which you find a solution which is continuous in time with values in L1, LR. Okay, so it stays in L1. That's not complicated. The PDE is conservative. The mass is conserved, but it stays also in LR. And okay, now the kind of solution that we consider are mild solutions. Okay, so that's weak form for the Keller-Segel PDE. So here, just to mention, so this is just the convolution with the Gaussian, right? This is the Lipson group here. What else can I say? Yes. So one of the nice things about it is that writing it this way allows you to put the divergence here, which was initially on the drift, to put it on the Gaussian here. Okay. So that's why you are able to talk about U in with that kind of regularity or absence of regularity, in fact, because you've transferred the divergence here. So, okay, so for this PD, I mean, this result only tells you local well-posedness. So I will talk about the maximal existence time. It may well be that this maximal existence time is plus infinity, but a priori, I don't know. It might be finite. Yes. So in fact, this is a quite general result. It works for a lot of kernels. It doesn't have to be Keller-Segel, but whatever. Okay. So now the particle system. So I just writing it again here. So that's the mollified one. Okay, the one with the mollified here. And I will consider also the objects. So the empirical measure mu n of this system convolution with VA. This I can do. I will just call this object UN. And I have an assumption on alpha. So remember, alpha is the one used to define again. And this alpha has to satisfy this. So it doesn't matter. You will see it in the next slide. Just to mention that I have a constraint on alpha. So of course it's positive. And I have an upper bound, okay, which depends on the dimension. And it depends on the value of R that I've chosen. R is the parameter here in which I'm looking for solutions. But this value, I don't comment on it. You will see it on the next slide. Okay, so our result is the following. It tells you that, okay, up to the maximal time of existence of the PDE, you have a convergence of UN. Okay, UN is my mollified empirical measure to U, which is the PDE. In this topology, in this norm, L1, LR. Okay. And this convergence is quantified, so it's upper bounded for any n by the difference on the initial conditions, which is the number here, plus here some rate. And the rate, I can explain it briefly. It's quite inevitable in a sense. So there are two quantities. This one here, it really comes from the fact that we have mollified with Vn. So it's a real bias, a deterministic bias between, okay, imagine you take a function f, you do a convolution with Vn, and you compare this to V in LR topology, okay? And you get this rate. Basically, that's more or less this. And this comes from the convergence of stochastic integrals. So typically it's rates in the law of large numbers for 1 over n times the sum of n stochastic integrals, okay, with independent Brownian noises in this L1 LR norm. Okay, so this is this for sure is sharp, okay, because it comes more or less. The only inequalities that you do to get this are Burke-Davis with these inequalities. You have both upper and lower bounds. Okay, and this one is a bias, deterministic bias. Just to explain a little bit, then I will show some equations if I have time, but at least the intuition for these two quantities is quite clear.
So, Alexandre, can you show the previous one? This one.
So the parameters that matter are alpha here. The bound which is here is exactly the one saying that this quantity is positive, so that this goes to 0. Otherwise, it doesn't go to 0. Okay. Okay, so we can derive then all sorts of propagation of trajectory propagation of chaos result, but I will not go too much into the details here. Another for those who are a bit familiar also with this question, an interesting point here, which differs a little bit from the usual results, is that you don't assume anything. There is no under initial conditions. You can choose whatever you like. I'm not even saying that this is going to zero. So it's better if it's going to zero, but it's really quantitative. So it may be that the initial conditions are not independent or whatever. Okay. Don't have to assume exchangeability. Okay. So here I don't want to get to the details. So just if you optimize a little bit on the parameters, you can see that you get a rate. The best rate that you can get is for this kind of Keller-Segel models, 1/2 d plus 1. Typically in dimension 2, you get 1/6, which is also good in a sense because this holds for any parameter chi. Okay, I've not made any assumption for the Keller. Can be the bad Keller-Segel model. Okay, the one that blows up. It's still the same rate. Okay, my result would be true. Our result would be true up to the maximal time of existence. But it works for any value of k. Okay. Okay. So we'll sketch a proof a bit later in the case where I have the logistic, the suppression of law. Are there any questions?
Maybe for later. No,
Yeah.
because I mean, if you measure the distance, I mean the actual distance in a, I don't know, probability.
Yeah. We can derive.
Yeah, for the without regularizing.
Yes.
I mean,
Yes.
Would you expect to have convergence up to the blow up because it's a, I mean, you lose LR regularity, but you're still a measure. So
Yeah. So is that I'm not sure. I'm answering correctly. I'm interpreting correctly the question, but for the same particle system, the one which is modified. I'm only talking about the one that is modified, but I don't have to modify the empirical measure. I can consider directly the empirical measure, and this I can prove that it converges. So we had bounded Lipschitz distance towards UT with the same rate. But in fact, this is really a direct consequence of this convergence. You just bound the bounded Lipschitz distance by this one.
even up to the blow up.
Yeah, up to the blow up. But it doesn't. The particle system.
Yeah.
It's always well defined. There's no blow up in it. So the only constraint comes from this guy, from the deterministic one.
Yeah, but still you have the exponent of n depends on r. So if you lose
the exponent,
I was just if you really have a blow up at finite time for the PDE,
yep,
you will not have the convergence in LR.
Yes, because it's for t smaller than
yeah.
No.
If you could
okay, yeah, sorry, yes, you know. Okay, no.
Without the
no. Okay. No, because what? Okay.
Because
there is blow up. If there is blow,
sorry.
If this one goes to infinity.
Yeah.
So no. Yeah, definitely. I mean,
yeah, but
that would be we would have to work much more to say.
That's what my question was. Maybe for considering bounded Lipschitz distance directly on the empirical measure.
Yeah, you don't have LR, and then maybe things are possible. But okay, what I was referring to is really a direct consequence of this, so you will not see what you would like. I agree. Yeah, definitely. Okay, so now so the term is already appearing here, so I will explain. But okay, I'm considering now the case where I want to suppress the blow up. Okay, so I have this term here. So this one, in fact, is quite harmless. The one that is really interesting for us is this one. Okay? So that's the Keller-Segel PDE, and then I had these two terms. So at the level of the PDE, this new UT, you can interpret it as you're adding mass, in fact, your density. So when I do this, that means that UT is no longer has constant mass. Okay? This will add mass to the solution, and this the opposite. It removes mass from the system. So there's competition between the two. And so the first result that we derived, which is so inspired by a previous work by Theo and Winkler here. So it's purely PDE results. It says the following. So here, yeah, okay, mu and nu are always positive or non-negative at least. This is in dimension 2. Okay, here the assumption is slightly stronger. The initial density is bounded. And what we are saying, so the first part here is exactly the same as before when I didn't have this, just saying that I have a local solution, local well-posedness. It's a fixed point argument as well. So it's the same. The really interesting part is this one. It tells you the following. If mu, so this guy, is larger than d minus 2 over d times chi, so chi is the attraction, the attraction strength. So if you have this relation, then Tmax, the maximum time of existence, is infinite. So you have global solutions, so no blow up, right? So this. So there are several interesting facts here. The fact that mu plays absolutely no role in this story. Okay. So nu adds mass in terms of particles. It means that you have more and more particles, but in fact, it's not a problem if mu satisfies this. And also, what you see that in dimension 2, this is 0. That means that for any positive mu, you will have suppression of blow-up. So no blow-up in the Yes.
This is for all new, right?
Yeah, exactly. So here, mu just has to be non-negative.
And the conditional mu?
And mu does not appear here at all. No, it doesn't be there. Okay, so let's try to interpret this at the level of the particles. So, like I said, this term, it means really that you add mass to the system. So we will interpret this. This is quite classical for particle systems. We'll interpret this as particle so there will be bursts of particles at some rate nu. Okay. And if you have this interpretation, it's quite reasonable to say that this term will be interpreted as death of particles as with rate mu u. Okay, so mu u, it means what? It means that your rate of death will be proportional to the local concentration of particles. So let's try to have a look at what this is. So here I cheated a bit. So these are one-dimensional Brownian motions. So I didn't put any interactions between the trajectories. These are independent Brownian motions. The only thing that I do, so there is kind of interaction. So the blue points are bursts. So when there is a burst, I mean that okay, this particle here stops to exist. Sorry, and then I have two independent particles that appear. And the red crosses are deaths. Okay. So, like I said, here the death happens with a rate proportional to the local concentration. So that means that, while since here you see that you have several paths that are very close, you are likely to have a lot of death, which is more or less what we see in that region. Okay. So that will be the process we'll be using. So it's exactly what's written here. Fine. And now, if I want to be a little bit more precise, I will write it like this. So I call lambda n the set of all particles who are alive, those who were alive, and those who will be alive. And I give myself a Poisson random measure on R plus times ln times R plus. I will explain the labels. So for a particle k, which is in that set, okay, I need to describe when it appears in the system and when it leaves the system. So it appears in the system when it's being given birth. So either it's an initial particle, or it will be born at some time, which we call T0k. If it's born, it means that it has a parent. We split it into. Okay, so that's my T0 K, and then I need to describe when it dies, and it dies either when it divides, if it divides, or if it's killed because it's in a region which is too crowded. That's the minimum of these two times that I can write like this. So it's the infimum of the times, so the dash time of division, let's say, okay? It's the first time after T0K, such that this Poisson measure on this interval times K, so that's the label for particle K, with intensity mu, is different from 0. So you record the first jump for this, this Poisson measure, and you say that at this time, this is T1 and K division. Same for the death, except that here you need to be a little bit more subtle because the intensity depends on the local concentration of particles, which is recorded by the fact that you see here, this is why it's written in integral form, you have here the density, the local density of particle around xk. Okay, but this is at least locally this is an intensity which is proportional to. Okay, so same notations as before. I mean, almost here. So capital N is the initial number of particles, because like I said, and you've seen that there will be birth, there will be death. So the number of particles now is random. Okay, so IT is the labels for particles which are alive at time t. So it's a random number which depends on n. So now my empirical measure, it's really a sum over the particles which are alive at time t. Okay, and as before, I do a convolution with Vn. And the result is it reads similarly to the previous one. So up to the maximal time of existence, you get a convergence. So in L1, LR again. So you still have this term here, and you still have the rate of convergence here, which is almost the same as before. Almost the difference comes from the fact that the rate of convergence, so you have ions now in your dynamics, and they don't go to 0 exactly at the same rate. Not very far. So if you have been paying a lot of attention, there's another difference which is more subtle. It's like the fact that now the supremum in time is not inside. Okay, before there was expectation of the sup in time, and to be fair, it seems to be difficult because of the jumps to have it inside. Okay, so by the way, how much time do we have? The first thing?
20 minutes.
20 minutes more?
Yes.
Okay. So just tell me if this is too heavy in terms of notations, but to give you a flavor of what's happening here, we are really trying to compare UN directly to U and to have a Grunwald argument going on. So the first thing, of course, is to write an equation on UN in the same form as the mild equation that we had for the PD. So we do the same. So we will apply Ito's formula on this function evaluated at each particle. Okay, so this is this function. There's no difficulty here. And then, of course, so you do this for each particle. Then you sum all the particles, you divide by n, and you have UTN at point x. So x is fixed here. Okay, that's y in which you plug your particle. So you do this and you get, okay, you shake this a little bit and you get this equation. And so this M and J, so this is the continuous martingale part, continuous stochastic integral part, sorry. And Jn is the jump part. So when you do this, okay, when you do all this, in fact, mostly what you will get is this. This comes from the fact that I compensated the Poisson measure here. Okay, so I get this compensator part here, which you almost recognize in the PD. Okay, so now if you look a bit closely at all this, what do you have? So this is the same as in the PD. This starts exactly the same as in the PD. And then, okay, so yeah, I have K star UN already, that's good. But then as a little twist, here I have mu n, and here it's Vn at x minus dot. Of course, if this was a kind of a Dirac, I would have u k star u, so I'm almost good, but not completely. Okay, and same, more or less the same here. Mu n against Vn is almost un, so I almost have mu un minus mu un squared, but not exactly at the same points. Yeah. Which is really because of the convolution here, the fact that Vn is not local. So I almost recognize the PDE here, and then I have these two martingales, okay, which I expect to go to 0, but again, I have to work again. Yeah, say martingale, but these are not martingales, in fact, which is what we are paying here. Okay, it was nice to have this convolution with the Gaussian. So that gives me convolution integrals in time, but I have the same thing, obviously, on Mn and Jn. I have convolution in time here, which means that these and these are no martingale effects. Because you have the time dependence here inside. Okay, so these are not martingales, so I cannot directly conclude that not so far. Okay, well, this slide is just to say we don't need to look at the details. It's not interesting. What it just says is that I will introduce. So remember, I had this kind of terms, but what I would like is really this term. Okay, so I introduce virtually this term. I put it here, I put it here. Okay, so I do this on all the terms, and in the end, what you understand is that okay, this should act. I can have my control argument working on here, and this is an error term, and this is exactly the bias, the deterministic bias that I was talking about earlier. Okay, if I work a little bit, this I will have exactly the error I was talking about. There's no probability here. This is really an approximation result. It's not very surprising. Okay, same here for the computation of the jumps here and here. And so what will give me the rates really is, okay, of course, these two terms, which are pretty much the same, and the rate of convergence of the two stochastic integrals. So once you have seen this, almost done. So you have some a priori estimates to get. I skip this. Like I said, there is still a technical part to deal with. Is how to deal with this kind of integrals. Okay, so this is not a martingale, so we cannot apply directly to Folger Davis-Gundy. But so the trick here is to freeze one of the two. So typically we freeze this one. Then you have again a martingale. Okay, and then you can make things work, but you will pay the fact that the supplement in time is not inside the BDG inequality. So there are some things like that a bit annoying. But apart from that, also the other part is that this is it's a BDG in infinite dimensions, because here you integrate with respect to one of the parameters. So you play a bit with this kind of problems. But fortunately, from SPD theories, we have all the tools we need. Okay. You have to be a bit careful. It doesn't work for L1, for instance. So there are in practice, there are a few things which are a bit annoying, but okay, we managed to go through all that, and in the end, you get the rate that I was talking about, which is sharp. Now again, I can have the same overbound here. Okay. Questions? Okay. So the last part, I will say a few words, will be a bit less formal, but some recent work that we've been doing with Johan Tardy at Prague Polytechnic, Milica Tomasevich also there, and Sham Gopat with postdoc there also, on collisions for the Keller-Segel equation. So, like I said, in this one there are no collisions, no? Okay, so it's not this one I'm talking about. It is this one without modification. Okay, so I'm back to the bad guy somehow. I'm talking only about dimension 2, which is one we can really say interesting stuff. So it's not modified, so it's really this one I'm talking about. Okay, so you see the parameter chi here, which is very important. Here it's the kernel, the Keller-Segel kernel, which has been written explicitly. Each particle has its Brownian noise, independent Brownian noise. Okay, and the story that I was talking about at the beginning, this comes from the latest developments are in this paper. And what they proved is that, okay, in the supercritical regime, so that means when there is blow up, so in practice, that means chi larger than 4. If you fix a number of particles n, which is larger than 3 chi over 2, or whatever, in any case, you're interested in large n, but okay, you have to fix it like this. And let me call k0 this thing here, so 4n divided by chi, sorry, very explicit. I take the upper integer part. So for this k0, well, you have exactly k0 particles who collide at the time of explosion of the particle system. Okay. In fact, they have even sharper results in terms of there are two collisions which occur, which are harmless in the sense that they don't stick the particles; they live their life after that. And in fact, after this k0, before this k0 collision, you have k0 minus 1 collisions occurring, but they are non-sticky, and k0 minus 2, and nothing between 2 and k0 minus 2. So that there cannot be 3 collisions, for instance. 1, 3, 4, 5, whatever, until k0 minus. So that's a different story again, but that's quite fascinating, I believe. And of course, okay, so our goal was not to work on that directly, but to say, okay, in a case where we have this killing mechanism that we have studied in the regularized case, well, okay, now we consider the non-regularized case, and we say, okay, we will use the same death mechanism. Can we prove that there are no collisions now? Okay, or no bad collisions appearing? Okay, if I start to kill the particles when they get too close, can I avoid these critical collisions? So in fact, if you think about it 2 minutes, the direct answer is no. Okay, so there's randomness. Your killing is random. Okay, so it may happen with very small probabilities that the Poisson measure doesn't trigger, and so you have collisions, and then you're exploded. So there will always be, for fixed n, there will always be a very small probability that things go wrong. And so, but still, what we are able to say, so we explain here, is that we can prove that as n goes large, the probability of critical collision is extremely small. That's a free movement. Okay, so that's our latest results, and just to give you a flavor of how to do this, because now, okay, you have to deal with particles being very, very close. So we worked with this functional of the empirical measure. So the idea was to count the number of particles that are close, in some sense. Okay, so since we want to do some stochastic calculus, let's say, it's better if we can have a functional which is smooth. Okay, just imagine you want to do a close formula. You cannot just have something which tells you 1 if the particles are close, 0 otherwise, this will not be smooth enough. So we worked with this one. So you fix some parameter epsilon. And so you see here, if 2 particles, if I and j are close, this is close to 0, epsilon over epsilon, this is 1. Perfect. If they are a bit far away, sort of, then this is more or less small and doesn't count too much in the cell. So this is really a way to count how many particles are close. And it turns out that this functional is very convenient. It's a bit tricky to work with, but it's very convenient. It's not so complicated, but you have to work a little bit the details. What I'm telling you, and you can believe that, is that there cannot be critical collisions if this quantity is smaller than this. Okay, it's for the same k0 as in the previous slide. So k0 depends on n, careful. But here I work with fixed n. So if this functional is smaller than this quantity, then there cannot be critical collisions. Okay. I cannot have k0 particles which are close, in a sense. They cannot have collisions. So that will be my starting point.
With the fraction of the particles.
Yeah, so it's
The upper bound is K0 over n.
yeah, but K0 over n.
So if that fraction is, but you're not saying that it's small.
No, I'm not saying that this is small.
So it's an upper
It's
bound.
again, it's a bit difficult because IT is not n. I mean, the cardinal is not n, but it's close to n. So this is not between zero. The whole thing is not between 0 and 1, but you kind of think that it is between 0 and 1. It's not approximation.
But K0 over n means something.
Yeah, K0. Okay,
It should mean something. K0 over
K0 over n is more or less 4 over chi.
Okay.
Yeah. So you see, when I'm talking only about chi larger than 4,
yeah.
if chi is smaller than 4, there will not be any blow up. That's so I'm talking only about this quantity 4 over chi, which in that case is smaller than 1. Okay, so it's more or less the fraction of corresponding to 4 over
This
chi.
And there is an explanation for the number 4.
Oh yes, it's scaling. So if you go from one paper to another, it will be 4, it will be 3, it will be 8 pi. Depending on
the
yeah, it's always the same scale.
Yeah.
It's related. So if you ask to people who wrote this paper for the Jordan and so on, there is really an interpretation in terms of the dimension of the Bessel process. Okay. For this. Okay, so the good thing here now is that I can do some stochastic calculus from this guy. So I will. So that's where it starts to be painful. So okay, of course I'm not going to give you more details about this, but because this is just long and painful, yeah. No. Okay, and so yeah, just also to tell you that this is an interesting also consequence of this. I think it's nice on its own, but an interesting consequence of this is that you can also deduce propagation of chaos for this particle system without modification. So the big difference here is that there is no rate of convergence. There is another major difficulty, which is that this is only along subsequences, but this is kind of no problem. And so, okay, just to show you this this part here, what it looks like. So without entering the details, but like I said, you have an inequality on your functional. You have the initial condition. I'm not detailing all the parameters. The point is that you have these terms here, which takes you back. Okay, and the point is that, and you have other terms that tend to push you up, but if you play nicely, and there are some parameters that I didn't even introduce, if you play nicely with parameters, this term will win, and you can prove that you do not go, and of course you have a stochastic term, okay, which has jumps also and so on, but as n is large, it's supposed to go to 0, so you're more or less back to an ODE, in fact, or an ordinary differential inequality that you can manage. Okay. The conclusion would read like this: if you fix an epsilon and a t time t, any time t, okay. Well, you can start with any number of particles large enough, and the probability that there is a critical collision before time t is smaller than 2. You can make this as small as you want. In fact, this is quantified. I didn't try to write it. It's almost exponential. exponentially small here in terms of number of particles. So this is quite interesting. So okay.
Is there some sort of monotonicity in N or nothing, or just like?
Yeah, so
Because
so this epsilon, it's explicit in N. So it's all, so in fact, we have polynomials, maybe we can optimize a little bit. Let's say it's almost like exponential minus n, sorry, to some power. Okay. Or let's say n to the minus some power. As large as you want. And from this, yes, you can deduce convergence of the empirical measure to the Keller-Segel. So very weak form of the Keller-Segel PDE, which we are not good enough to prove. It seems to be difficult because there is uniqueness in this sense for the PDE. And so it's only along subsequences that we have convergence. You have all sorts of problems of that which are kind of nice, but difficult. Okay, so I will not mention there are quite a lot of extensions of these works, in particular in the moderate framework. And here are some references, and I thank you very much.
Are there any questions? Yeah. The first part?
Yeah.
Where the okay, I didn't get is the rate at the end. So okay, it comes just from the seeing what's going on with the marking games.
Yeah, so maybe it's better.
It will be related to the rate related to the convergence of empirical measure towards its law, or it's rather propagation of chaos like
It's really the rate of convergence of this guy. The n to the power blah blah blah. It's exactly the rate of this guy.
Yeah, but that guy, what is the rate? The rate is related to the law of large numbers for empirical measures. It's the level of empirical measure is at the level of particles. Like
no, okay. It's really about. No, here it's.
You're not coming with some independent particles.
No, here I use the fact that the WKs are independent.
Yeah, but just at that level. Okay.
Yes, just at that level. Here I don't care that the particles are here; they will disappear anyway. Okay. Because when it would be DG, you just just separate the only independence that matters is this, and then this is an LR norm, so it's invariant by translation. So this will just go away.
Yeah,
I don't know if that answers the question.
Okay. Yeah. Yeah, it's a level of the okay. And for the other one, for the jump one.
So just to complete maybe also, but we can prove also a propagation of chaos at the level of the trajectories. That's your question.
I mean, if we're using that or not at some point.
No. We can prove it at the level of propagation of chaos at the level of trajectories of this particular system, but in fact when we do that, we don't have a rate.
Yeah.
It's a different non-linear martingale problem. It's not at all the one that I presented.
But in terms of the exponent of the convergence, it would be similar to, because you will have you have a dimension dependence, so it's kind of
yes. It comes from also from the fact that you have gradient of Vn here. So you pay it you pay it somewhere. Yeah. Even if you can put it here if you want, you will still pay it a little bit, because even if you put that here, which you are allowed to do, it stays impeccable in time. But then you still have in the end the LR norm of Vn. So you pay a little bit, you pay a positive power of n, okay, which then you compensate by the fact that it's 1 over n times. So you have this 1 over square root of n, but you lose a bit because of that. The LR. If we could work only in L1, certainly the rate would be better, but we cannot close in L1 because the technical thing I didn't mention, but you do need some regularity on K star. So for instance, you want this. And a typical inequality on case with the L infinity norm of K star F is that you can bound K star F in L infinity by the L1 LR norm of F. And that's why we are constrained to work in LR, not just in L1. Yes. This K, the convolution gives you some additional regularity, but you have some needs and regularity from this guy. The balance between the two.
And for the last part, so you're suppressing particles.
Yeah. Sorry, so I was a
Way.
bit far, but so that's what happened for the particle between birth and death. But yes, then sorry, yeah, I was really too fast here. The particles that appear here, I'm applying the same rule before, so they will be given birth at rate nu, and they die at rate mu un. So same as before. So these particles they exist between two random times only, which is encoded in fact in this index here IT. But yes, sorry, it's the same mechanism. Yeah.
Okay, so in the end, they are not colliding because they are being
We cannot rule out completely that they collide. But if they do so, it's certainly not with probability 1.
But the fact that they do not collide is because you remove them.
Because we remove them very hardly, very quickly as we can, when they are getting too close. Like I said initially, that cannot be enough. Like there are still very small probabilities that things go wrong. The things that work perfectly is only at infinity. I mean, only at the PDE level. And this, I don't. Maybe our bound here is not optimal, but the result you can never say that this is 0. So I cannot imagine this.
Other questions?
Can you take mu to 0?
What do you mean? So
Like the like have some sort of viscosity or something like that solution where your healing goes to 0.
So for sure, like all the computations are explicit in terms of mu, but I don't know what this would tell you, because you know that for mu equals to 0, for mu equals to 0, you know that there are critical collisions, because there is a kind of phase transition, very brutal phase transition. So I don't know what's maybe at the PDE level.
Yes.
I have no idea what this is. At least I will start.
Are there any further questions? Line or inline? No. Thank you.